Hello and welcome to today's tutorial. So today we're going to talk on the autocovariance and the cross correlation of random process. So let us take the first one and switch back to our screen here. So now let us see what is autocovariance. So we will use the autocovariance function when the mean is not zero. So we can write from this definition, if x of t is a random process with a non-zero mean, then it may be convenient to define an autocovariance. So the mathematical definition of autocovariance is defined as Cx of tau is equal to an expectation of x of t minus mu x of x of t plus tau minus mu x. We know that the mu x of t is equal to mu x, it's a constant. So when you open up the bracket and simplify this here, the mu x square terms will get cancelled. So ultimately we will get the autocorrelation of tau minus mean of x square. So this is the covariance mathematical definition. So next we'll talk about the cross correlation. So now let us talk about the cross correlation function. So cross correlation is nothing but if we try to find a relation between the two different random process, so that relation we call it as a cross correlation function. If we define it as a function, we call it as a cross correlation function. So now we have considered the two random processes here, that is x of t and y of t, and both are considered to be a white sense stationary. Then its cross correlation function mathematically can be defined as rxy of t1 comma t2 is equal to an expectation of x of t1 into y of t2. So from the previous definition, we have taken this t1 is equal to t. We know that the instance where we are taken the n symbol average, the beginning point itself, the t1 we call it as t, and the difference of those two instants of time, that is t1 and t2, the difference we represent it as by tau. So tau is given as t2 minus t1. So now if we substitute that again in this equation here, so then we'll get rxy of t comma t plus tau, which is equal to rxy of tau. So that expectation, so that will become an expectation of x of t into y of t plus tau. So this is the mathematical definition of cross correlation function. So now now let us look into the properties of this cross correlation function. So like autocorrelation function, we have rx of minus tau is equal to rx of tau, but here the case is different. It is not symmetry. It is not even symmetry. Why? Because it is rxy of minus tau will result in ryx of tau. So it is a different case here. So that you have to note at this point. So this is one of the property. So now the another property is that from this same equation 1 we can take. So when we apply an expectation for this, so then we will get a mean of x of t with a mean my of t here. So it is a mean of x with mean of y. And the another property is that, so if y of t is a periodic with a period t, then what happens to this cross correlation function? It is same. It means after every time period t, the same pattern will repeat. It means the cross correlation function is also periodic. If a random process, any one of the random process is periodic, say in this case if it is y of t is periodic, then its cross correlation function is also periodic. That is what it means. Also, if x of t is a periodic with say period t, with fundamental period t, then its cross correlation function also results in period t. It means after every time period t, it will repeat. That is ryx of tau minus t is equal to ryx of tau. And the one more property is that the cross correlation function, so this we will get from the bound. So this we have shown in the next clip here. So in the next screen we have you will see this proof of this. So right now just take this as rxy of tau is also less than or equal to the square root of the correlation of x with correlation of y at tau equal to 0, that is square root of this. And the one more definition is that it is also less than or equal to half of correlation of x plus correlation of y at tau equal to 0. So these are the properties of the cross correlation function. So next we are going to see the proof for this bound case. So now let's see the bonding case. So there are two bounds on a cross correlation function. So that is defined by an expectation of x of t plus k y of t plus tau whole square, which should be greater than or equal to 0. So when we apply this a plus b whole square formula, we will get this equation where it is rx of 0, it is plus or minus 2k. Here we will get a cross correlation function, that is rxy of tau plus k square into ry of 0, which is greater than or equal to 0. If we consider the first case where k is equal to 1, then we will get the relation as the bounding relation as rxy of tau is less than or equal to half of rx of 0 plus ry of 0. And if you apply the value of k equal to 2, so then we will get the next case. So let me take this here. This page is 15. So here for this is for k is equal to 2. If I take the value of k is equal to 2 in the same equation, and when we substitute this, then we'll get a square root of rx of 0 into ry of 0, which is less than or equal to half of rx of 0 plus ry of 0. So these are the bounding conditions. So now let us look into the cross covariance definition. So mathematically, the cross covariance definition is defined as cxy of tau is equal to an expectation of x of t minus mu of x into y of t plus tau minus mu y. So when we open up the bracket and simplify, then mu x y terms get cancels, and finally we will get only the cross correlation function of tau minus mean of x into mean of y. So this is the cross covariance function. Now let us see the examples here. Yeah. So let us take an example. So let v of t is equal to x plus 3t, where x is a random variable, and here the mean of this random variable x is equal to 0, and the mean square of this random variable is equal to 5. We have to prove that the expectation of this v of t is equal to 3t, and the autocorrelation of this is equal to 5 plus 9t1t2. So let us take an expectation of v of t. That is, v of t is nothing but, from the definition, it is given as x plus 3t. So when we take an expectation, so 3t is a constant, so here we'll take expectation of only x. So when we take an expectation of x, we'll get mean of x. So from the definition, it is given here, that is mean is equal to 0, then finally we'll get this as 3t. And when we apply the autocorrelation function here of two time instants t1 and t2, then an expectation of x of t1 with x of t2. So we'll substitute here the v with respect to t1 and t2. So when we open up the bracket, we'll get this, and we can see here that the expectation of this x is, that is nothing but the mean of x. So mean of x is 0. Here also this term will get 0. So finally we will get only the term 5 plus 9 t1 into t2. So that is what it was asked to prove, and we have shown that. So let us take one more example here. So let the two jointly Whitesand stationary random process have the same function of form x of t and y of t, and x of t and y of t are defined here below. That is, x of t is equal to a cos of omega naught t plus theta, and y of t is a b cos omega naught t plus theta plus phi. And here a, b and pi are constants, and theta is a random variable which is uniformly distributed from 0 to 2 pi. Then we have to find the cross correlation function. So the cross correlation definition is an expectation of x of t into y of t plus tau. So we have substituted these cos terms for x and y, and to find these expectations, so now this is x and y terms, so we need a PDF also. So since theta is our random variable here, which range from 0 to pi, so that definition is given as f theta of theta is equal to 1 by 2 pi. So when we substitute that in this definition, so then when we substitute in this term and when we integrate here, so basically here we have applied again cos a into cos b formula. So we'll get a cos a plus b plus cos a minus b. So we have interchanged the first and second term here, but that doesn't make any difference because in between there is a plus here. So now in this term we are integrating with respect to theta. So let me take this to my screen here. So that this is page number 18. So I'll take this page here. Okay, so it means when I write here it is a into b by 2. So expectation definition is nothing but it is, say, from minus infinity plus infinity. So now here the limit is from 0 to pi. I think that is what, or pi to 2 pi. What is a question that is given? It range from 0, yes, is 0 to 2 pi. So now here we have our cos x term, that is a cos of omega naught tau minus phi into 1 by 2 pi into d theta. So now we have to integrate with respect to d theta. So likewise plus an integral of 0 to 2 pi into cos of this 2 omega naught t plus 2 theta minus omega naught tau plus phi into 1 by 2 pi into d theta. So here there is no theta term, so this has become a constant. So whereas here there is a theta term, that is 2 theta. So this, when we integrate this, we will get a sine term here, and when we substitute these limits sine 0 and sine 2 pi, it will be 0. So ultimately this term will result in 0. So we have only this term, and we are integrating with respect to d theta. So then we will get here the terms, so that you can see from here. So finally we will get only ab by 2 into cos of omega naught tau minus phi. So this is what we will get here. So now let us take one more example here. So hopefully I think it is not saved. So let me save this page and take the new page. I'll give one example as a homework for you to work out. It's a very simple example. So the random variable x has a uniform distribution over, say, 0 to 2. Then we have to find mean and mean square for the random process v of t. I'll define that v of t here. So that is v of t is equal to 6 into e power xt. Okay, so and the value of x range from 0 to 2. So for this the PDF definition is given as, that is fxt of x, for this case it is equal to half for the value of x ranging from 0 to 2, otherwise it is 0. So now here x is equal to, or v of t is equal to, now it is 6 e power, oh, not this, let me erase this. So now it is 6 into e power xt. So let us take the expectation. We have to find the mean. We know that the mean of x of t is equal to, this is a capital X here, the random process, so v of t. So this is x of t is equal to v of t, we can consider. So anyway, so just integrate this term 0 to 2 into, I am solving this anyway, so we'll just substitute t with, now the PDF definition we have to solve it. This is integrate with respect to x. So finally after integration we will get this as 3 into e power 2t minus 1 by t. So integrate this, so e power xt we will get e power xt by t. Substitute the limits, that is 0 to 2. So likewise, in the expectation of x square, we will get like an integration of 0 to 2, that is x square, then it is fx of t of x. So substitute, then I'll straight away write the answer, that is e9 into e power 4t minus 1 by t. So this is what we will get here. So next we talk about the addition of random process. So if we add two independent random weights and stationary random process, so what do we get? Let us see that. Let me save this page here. So let me give it as 21. Take the new page. Addition of random process. If we add two random process, what do we get? So let's see that. So before that, we consider a case that let the two random process be independent and the two random process be independent and jointly wide sense stationary, that is x of t and or y of t, then what do we get? So that will lead to a new random variable, that is w of t, which is equal to the sum of x of t plus y of t. So let us apply this, let us apply autocorrelation function for w, then see what is the autocorrelation function that will result for this new random variable, new random process. So let us write this as Rw of tau. So then from the definition, Rw of tau is nothing but an expectation of a random process, that is W of tau into W of tau, W of t plus tau. It means we are taking the expectation of t with its shifted or the difference with respect to time tau. So now I will substitute this the w of t and w of t plus tau as x of t plus y of t. So then here I will get this as x of t plus y of t. So here we have x of t plus tau plus y of t plus tau. So now if you open up the brackets and take this expectation, then what do we get? So let us open up the bracket. So we'll get here x of t into x of t plus tau. So I'll get an autocorrelation of tau plus x of t with y of t plus tau plus y of t with x of t plus tau and y of t into y of t plus tau. So when we take an expectation of all this, then finally we will get this as Rx of tau plus, so if you say this is a cross correlation function, x of t with y of t plus tau and y of t into x of t plus tau. So both results in same, so I can write this as 2 Rx y of tau plus it is Ry of tau. So in terms of autocorrelation function, if we add the two random process, that is x of t and y of t, so that will result in the sum of the autocorrelation of x with autocorrelation function of y with the cross correlation function, the twice the cross correlation function of x and y. So that is the definition of it. So that's it. So now if we talk this x and y in terms of cross correlation function, what do we get here is that the cross correlation function, we will get this as we will get only these terms. Just a minute, hold on, because if x of t and y of t are independent, the cross correlation simply it is Rxy of tau is equal to, so what is the cross correlation function defines? X of t into y of expectation of x of t with y of t plus tau. So if we take the, let me save this page here. So this is page 22, and let me take the new page here. So if we take the cross correlation function, so by definition that is Rxy of tau is equal to Ryx of tau, which is nothing but we will get here the mean of x with mean of y. So if we look into the previous equation, if one of the mean is equal to 0, then finally we will get the cross correlation function, that is Rxw of tau. We will get this as Rx of tau plus Ry of tau. So this is the addition of two random process. Now what happens if the two random process are multiplied? So let us take the next case here. So let me clear this screen. So let me write here, that is multiplication of random process. If you multiply the two random process, two independent random process, then we get W of t is equal to x of t into y of t. So with the mean of this, if I take an expectation of this W of t, so then expectation of this x of t with y of t, I'll get here that is mu x mu y. Then the variance if we take, then we will get sigma w square is equal to an expectation of x of t with y of t minus mu x mu y whole square. So that is given by the variance of x plus mu x square into the variance of y square plus mu y square minus mean of x mean of y. So if we see this in terms of the autocorrelation function, then what do we get? So if you write the Rw of tau for this multiplication case, so then this is equal to an expectation of, say, x of t into y of t into x of t plus tau into y of t plus tau. So this results in nothing but if you group these terms like this, that is an expectation of x of t into x of t plus tau, then an expectation of y of t with y of t plus tau, then we will get, like I'll write here, so then we will get here, that is Rw of tau is equal to, it is Rx of tau into Rx of tau into Ry of tau. So you can see from this definition that it is a product of the autocorrelation of x with autocorrelation of y if you multiply the two random process, and if we add the two random process, then it will lead into the sum of the autocorrelation of x with autocorrelation of y if the mean is equal to 0. Otherwise the cross correlation will come into picture there. Yes. Okay, then thank you for watching this tutorial. So catch me in the next tutorial. In the next tutorial we're going to talk on the ergodic random process, and yeah, we're going to talk on ergodic random process and the power spectral density. So thank you for watching this tutorial.